Hey everyone, thanks for coming this October. This is our 12th PWLTO, so we've had a whole year of meetups. Today we have Suhail. He's going to talk to us about the topic of reflection.
Thank you. Can you guys hear me okay?
Yeah.
Okay. So first of all, just a caveat, there was a reason that I was running late, and that was my presentation that I created nicely on my home laptop. That crashed. I had to rush back home, grab a new one, and I put this together. This is sort of my first version that I started creating a week ago, and I managed to update it. But if the slides are a bit bumpy, apologies in advance. I'll try and fill in the gaps by going back to the paper and pointing out examples there, and we'll carry out a discussion. I just want to get sort of a feel of the room. How many people have read the paper, actually made the way, skimmed the paper in any manner? Okay, skimmed it slightly, a little bit. Okay, cool. So, yeah, put it right there. I also want to get a sense of like what is the background like? Are people familiar with sort of recursive data types, like data type in the sense of algebraic data type? Can I get a show of hands? Okay, most people are. Excellent. Cool. So then this would be kind of quick, which is also bad for me because that means more time on things which are not good slides. So the essence of the problem, right? This paper goes all over the place. A lot of the things that the paper talks about, the problem that it addresses, it's essentially a performance issue, but it's a performance issue which is an algorithmic performance issue, right? And it provides a fix for that. But because it sort of phrases it in a context where it's applicable to many different scenarios, it is applicable to scenarios sort of list appends, to free monads, to monad transformers and things like that, to effects, tying back to discussion papers we love that we had, I think, a couple of months ago about algebraic handlers. So the applications are quite diverse, but if you were to focus on what is it really talking about, the basic essence is, in all these contexts, there is some recursive data type that is there, and I'm going to sort of step through these points for the benefit of those who are not familiar with these terms, and even for the benefit of others, for us to ensure that we're talking about the same thing. There needs to be an associative binary operation. I'm just calling it plus here, but it can be anything. The paper uses various forms of that, which has certain properties. And we'll dig into that. It has a couple of properties, and then given that, it basically says that if you were to take that set of operation, and it's a binary associative operation, the left associated view is performing worse than the right associated view, right? So even though the semantics don't change, the performance gets impacted just by grouping, right? So it's associative semantically, but it's not from a performance perspective. And then how do we fix that, right? So this is the essence of the problem, but let's go step by step. So the first thing it talked about was we want a recursive data type. Well, I'm going to take a step back and just talk about first algebraic data type, because I'm also going to introduce the Haskell syntax since the paper uses it, and also the examples that I have use it. So an algebraic data type has two components in it. In a sense, one is the type that you're talking about, and the other are sort of constructors. These are the ways that you can generate that type. There's another lens to it that you can unapply things and you can pattern match, but we'll get to that. So in this example, when we have, it says data human equals female string or male string. So the type is human. This is the type of this is the data type, the type of the data type rather. And the constructors are female and male. Each one of the constructors takes a string argument. This is the Haskell syntax. So if you're reading a data declaration, the first thing is the type. The things after that, which are separated by this vertical pipe, are the constructors. So the first would be the constructor name, and everything after that, before the next pipe, is going to be the type of the arguments that that constructor takes. So in this case, we can imagine, there are two ways to create a male, to create a human, and this is somewhat archaic. You can have mixed genders or other options here now, but you can think about the string just being the name, right? So you can say you can have a male, you can have a female, and those are the options. If you had a data binary, it could be 0 or 1, and that's it, and it doesn't need to take any constructor argument necessarily. Everything good here? Okay, so now we talk about recursive data type, and this is, you could see it wasn't fully deleted in the previous slide. My shoddy work from last week coming to haunt me. So recursive data type is, it's an algebraic data type, but there is recursion, which just means that in one of the constructors, one of the arguments to the constructor is the thing that you're using to define it itself. So butchered English there, but data list A, this is the data type. The data type is for all A, list A. Haskell provides sort of a succinct syntax. You don't need to specify for all A, you can if you want, but it introduces variables as you go. So the type is not just any concrete type, it's essentially a family of types. You can have a list of integers, you could have a list of strings, you could have a list of humans, you could have a list of whatever, right? For all types A. There are two constructors. One is the nil constructor, takes no argument. And then there's the cons constructor, which is essentially appending things together, right? This constructor takes two arguments. The first one is of type A, so whatever the entity object in the list is. So if it's a list of humans, then this would be sort of a human. If it's a list of integers, then this would be integer. And then you have basically the rest, the tail. And the tail is referencing, the type of this argument is referencing whatever it is that we're defining, right? So we started with list A, and we have a reference to list A here. So this is sort of a recursive data type. Anything good here? The only thing that I've changed is essentially a self-reference. Okay. So we've covered this first portion of recursive data type, and now let's look at the next portion, an associative binary operation. So they call it associative binary operation, but associativity is only associated with binary operations to begin with. So let's talk about what is a binary operation. Binary operation is a mathematical operator, any function which takes two inputs and produces one output. Plain and simple. You can think about mathematical addition, multiplication, list, and we can keep on going. There's lots of examples. Binary just means you have two input arguments and you're creating one output. So what is associative? What does that mean? It means that the groupings don't matter. So if I had some hypothetical, double plus operation, what associativity means is if plus plus is, or double plus is associative, if I were to do x and y first and then do z, that's the same thing as doing y and z first and then doing x. It is different from commutativity, because I'm not changing the order of the order in which I'm passing it to the operator. I'm simply changing the sequencing in which I'm performing these operations, right? So I'm not changing this order, but I'm just changing the grouping. All good here? Okay, so now we have to have some properties in here. Let me see if my next one. Oh, okay, so what do these properties mean? And I'm abusing notation here. I'm using shorthand. This big O, think of it big O, but really think of it as just rough estimate of what is the cost complexity of performing this operation. The paper doesn't go into is it big O, small o, is it theta, what is it? It's just trying to provide a sense. They use big O as a general sense in most of these things. So it's just a notion of we can use big O notation, and we can take this to mean big O notation. The property of this associative binary operation is that if I were to, and in this case is plus, so if I had two operands there, x and y, and I am performing this operation on it, the cost of this is proportional to the left one, right? It doesn't really matter whether it's left or right. Essentially, it's talking about that there's a bias. It's asymmetric in that, and it's this asymmetricity which becomes the essence of the problem, that one kind of grouping is better or worse than the other kind of grouping. Right, so if it were the fact that O of x plus y is y, it would still apply. This thing would just be reversed. The problem would still persist. We've changed our definition of left and right. That's the only thing which has happened. But then the second point is that x and y, the magnitude of that, whatever the output is, the size of the output, it is greater than the size of y. These two go hand in hand. And the reason, so I'll explain the reason of that. But what this is basically saying is the output of x and y cannot be smaller than or equal to just y itself, right? So we can be weaker than this. This is somewhat, this is the, I guess, we can put a stronger constraint. A stronger constraint would just be that this operation only builds things. It doesn't delete things. It doesn't collapse things. It only keeps adding things. And then trivially, this property is true, right? So, but the sort of more general condition would just be if this is order of x, if this is a function of x of the size of x, and this is greater than the size of y, then we will face this problem. And the problem is that left associative t is worse than right associative t. So are things clear at this point? Like, okay, cool. Really simple, nothing. Associate from the left side, do the left operations, start making pairs from the left side, start making pairs from the right side. Okay, so let's look at an example of what this really means. And the simplest example that the paper goes with, and by the way, associated with the paper, there is a website as well, which has other working examples, which introduces in more depth, or rather provides a more tutorial perspective. So that's where I've taken the code from. And I think for those who are more interested in the paper, I would urge you to go to that sort of website and just skim through that first, and then perhaps dig deeper through the paper. I only discovered that quite late after I'd read through the paper a couple of times, but that was quite useful. So in this case, we're looking at a recursive data type. Our data type is, again, our list data type that we defined. Two constructors, nil and cons. It's where the recursion is happening. And we're talking about an associative binary operator. In Haskell, this is syntax for type signature. This basically says, my first argument is a list, my second argument is a list, my output is a list. This is basically saying what you would expect it to say, that it's taking two lists and producing a list. It's somewhat wonky if you've never seen curried notation before, but that's not really the point. So here we've got this operation, x and y, and I'm basically, this is one way that I would define this operation. I'm doing sort of case match on x. So this is where I would pause and say that a lot of functional programming languages don't just use constructors as a way to construct the data type. They also see that as a way to decompose the data type. They don't necessarily have to go hand in hand, but a lot of the languages, especially SML, ML and stuff, they see these as going hand in hand. So if you can construct a data type in two ways, you can deconstruct it in two ways as well. So here I'm deconstructing x, my left argument, and there are, again, two scenarios here, right? It can either be part of the nil, it can either be a nil, or it can be a result of a cons. Because those are the two ways that I can make a list. So if it's nil, well, there's nothing here, so the result of appending is just the output itself. But if it is something here, then the output is, there's a head and there's a tail. The output is such so that the head is whatever this head is, and the tail is obtained by doing the append of this tail with whatever it is that I want to put afterwards, right? So basic list append definition, keep the head the same, append the two tails, append this list, the tail of this, with whatever the thing that you want after that. But an important thing is happening here, which we'll come back to later, is just the deconstruction. The definition of x depends and varies depending on the constructor. just knowing the type of X is not enough. Knowing the type of Y is enough, almost in a sense, because you don't really decompose or deconstruct Y. You don't really care if it's a nil, if it's a nil or if it's cons. And we can see X plus Y. What is the size of computing this? Well, we are repeatedly breaking down X, right? So, right. So the cost of doing X, appending X and Y is really just however large X is, because we will keep descending in this cons, and we will keep expanding this and again repeatedly doing the same operation. It will go back, if it's again a cons, it will go through this again till the time that you've broken X down, the first argument down, all the way out to the nil point, and then you just say, okay, this T plus Y is just Y, right? So this is the size of X. That's roughly, you can add in constants and stuff and multiply with some coefficient there. But this is what it is. And the size of X and Y is definitely greater than Y, right? Because the size of X and Y is X and Y, the size of X plus size of Y. We aren't deleting anything. And you will see that in most of the examples that it provides, that it just triply is true because you don't delete anything. But this technique is applicable to even a larger degree of cases. Okay. Right. So let's look at left associativity explicitly versus right associativity here. So I define a function left. It takes in 3 arguments, these x, y, and z. And I'm making it explicit. I'm making this sort of sequencing explicit. Haskell is a lazy language, so it's not as explicit, but I'm not put seek and stuff, but basically I'm saying, okay, if I have 3 inputs, x, y, and z, one way to do it, and this is what I'm calling the left associative way, would be to define, first compute x and y, group them together. This will take x number of steps. I'm calling it xy, and then take this xy and then append it with z. And now this will take xy number of steps, but xy is, the size of xy is x plus y, right? So total cost spent here is 2x plus y, right? So twice the size of x originally plus the size of y in this left associated view. Is that clear to everyone? Okay. On the right associative side, same thing, just do y and z first. You computed it, the cost here is y, and then do x append with y, z, and here it's going to be x, and the total cost here is x plus y, right? So that's where you're getting the savings here. And the reason that you've seen this different behavior goes back to the asymmetricity of the operation, of the fact that the cost of this only depends on one argument, right? And it's this left argument versus the right argument. And if we had an associative binary operation where the cost of this was depending on the right argument, right would be worse than the left associated view, right? So the fix would be sort of, CVS Transform would not work, but the fix that the paper applies would still work. But yeah, it's a nice exercise to go through. Okay. Cool. So what is a CVS Transform? How many people here are familiar with continuation passing style transform or? Okay. So I'm going to talk off CVS Transform, actually not going to reference and talk about what it is and how to get into it. It's really cool for those who don't know about it. There are lots of different applications. But for the purposes of the paper, it's only one very sort of special property of it that it uses, and it's looking at it from that very narrow lens and perspective, and that's all that I'm going to focus on, because you can go into depth in CVS Transform and the various ways that they can be used, and continuations and stuff, and delimited continuations, but none of that really applies or is of concern here. So the essence of CVS Transform, it can be X Transform, you can call it whatever, is when we are faced with this problem that the left associated view is bad than the right associated view, well, how would we fix that? One way is to provide primitives so that only right associated things form, right? And this CVS Transform is one way of doing this, right? So I'll explain how it goes about that. So it's simply a way to generate by default the right associated expressions. And why is that good? Because if things are right associated, everything is all nice, you don't run into that performance issue. The base data type, the CVS Transform depends on a base data type. For list, this is what the CVS Transform looks like. You would have a similar CVS Transform or the density transform for monads. There are various other things. They're simply generalizations of it. If you get this, you can then dig deeper into that and get the other aspects as well. But this really is the more important, or the essence of it, that we should, that if you can get this, then excellent. And so it starts with the base data type, and it creates a derived data type, which is right associated. So in this case, my base data type is a list, the same list that we talked about. My derived data type is diff list that I'm creating here. This notation is just creating it as a type synonym. I don't remember if I ran it. Yeah, no, this would be fine. You don't need to create a new type. But this essentially, this type says, and I'm using different syntax. I'm using Haskell's inbuilt list, but this is taking list A to list A. Think of it as a function which takes one input, list A, and produces one output, list A. That's what diff list is. Right, so I've created this derived data type, and I will also create two functions. One to go from the derived data type to the base data type, and one to go in the opposite direction. So going from a diff list A, getting a list A is simple. I've written the type signature here correctly, this was simply since this is a function, just apply it to something. The thing that you want to apply it to is nil. The diff list is functions, and the appends here become function composition. So you're making this entire big chain of functions. It's F composed with G, composed with H, composed with K, and you've got this entire chain of functions, which is your diff list, right? So instead of having elements on a list, you've got functions, a stack of functions now. And what happens when you apply nil is it enters right at the base of that, gets applied, gets applied, gets applied, gets applied, gets applied, all the way to the top. So this unwraps the full thing to the point that you get a list, and this takes order of magnitude of x, whatever the size of x is. So think through, you can go through this, but the important thing is going from the derived data type to the base data type is expensive. It takes order in sort of computation time. Going from the base data type to the derived data type is cheap. It is simply creating this function thunk. You don't really do anything, you just create this function and say, oh, I'm a function which whatever my input is, I'm going to specialize myself to some input, whatever, I'm going to take some list. So I've taken a list, and I'm a function which takes another sort of list, and I'm just going to sort of append it at the end, right? So because I'm just creating a function, I'm not doing anything, I'm not applying it, the cost here is really cheap. And this is a similar property that you will see in the final solution as well, where going from diff list to list is expensive, or rather derived to base is expensive, base to derived is cheap. Yeah.
What's the /t? Map is /t.
Oh, this is lambda expression, sorry. Yeah. So all this is saying is I've got an anonymous function. In Haskell, this is a way to define the function, which says this slash actually defines the function, and t is my argument to the function.
Okay.
Yeah. So there's a function. This entire thing is a function from. This is a comment, but from here to here is a function with input t, and this is the way it's being used. But pictures, because pictures are more fun and pictures are clearer, and they definitely help me. I was kind of going crazy when I started running through this and trying to really find the common thread. It's like, why does it really take what's really happening here? But pictures are fun. Okay, so how do we read this? First of all, let's just ignore this portion, this slide, I think. You want to yeah. Ignore that one. Let's focus on this one. In this case, I have x, and x, x0, x1, x2. The x stands for sort of the base data type that I'm using. This is my base type. 0, 1 is simply giving different numbers for the different arguments. This is my operation, my associative binary operation, and this is my output, right? So if my base type, this may be in list, this may be a list, this may be a list, this may be a list. It may be sort of monad, so monad continuation kind of thing, A to MB, B to MC, and I'm getting something else here, A to MC, and this could be class decomposition, but this is, these are all belonging to the same type. So this is the original view, and in list, this would be a list, and a list, and this is your list append, right? So what does the CVS transform do? So, or how would we use the CVS transform? So CVS transform takes that picture and transforms it into this one, right? We keep the x0, x1 on that side, we keep the x2 here. And what we say is, I'm going to create this internal representation, one which is more efficient, one which is better in some sense. And I have my toDiff function being defined, which goes all the way from, converts a list to a diff list. So it takes an x, converts it to an x prime type from base to a derived type, right? And we saw that, sorry about this, we saw that this thing here is cheap to do, right? So this is order 1. This gets done in order 1, this gets done in order 1 on this side. And then I define my operation that I want. Well, this was here, but now this is defined in terms of this, in terms of the derived data type. And this has certain, some complexity around it. In the case of CVS transform, this is function composition, so it's order 1 as well, right? So order 1 here, this is also order 1, you get here, right? Everything is nice, hunky-dory, we all good. And then finally, because we need to observe, have that form, so we are going from x0, x1, we need to create this x2. We need to run this from diff, but this is what's expensive. At this point, the entire computation is run, and this takes order in. But this entire process now has gone from this to that output in order n steps, right? And what we had here was, this could potentially be quadratic. I'm just going to jump back here to show you. Right. So in this case, when we had 2x plus y and we had x plus y, you may just think these are still sort of linear, but these things stack up. If x, because it's a recursive data type, it could be composed of such appends within it, right? So when we start thinking about having these operations nest one after the other, that's where this problem really emerges. And this then becomes, n steps plus n minus 1 step plus n minus 2 step plus n minus 3, so you run into quadratic complexity, which right associative continues to be linear. But this is what we see in this case, right? This is linear, everything is good. This was potentially quadratic. But there's a problem with this. There's a problem with the CVS transform. But before we go there, are there any sort of questions on this diagram? Nope. Okay. Either I'm doing a really good job or I'm doing a really bad job. Okay, so what is the problem with the CVS transform? The problem is we have defined this sort of append prime or plus prime in terms of all the prime sort of derived data type, right? And what did we start with? We started with something which was basing off of the base data type, right? But in this base data type, this thing can very well inspect x0. This thing can very well inspect x1, right? It can inspect and look within it and see if I need to do something different. But when we are creating this, the only way for this to inspect this or this is to convert this diff list back to, using the function from diff back to a list, right? Converting this derived type to the base type, and then I can inspect. But converting from a derived to a base is expensive, right? So for certain classes of such operations, you're okay. Those classes of operations which don't care and don't need to inspect within the constructors and do something special, you're fine. You're completely okay. But if you are running into problems, places where this operation actually does things differently by looking within, then the CPS transform is not going to save you, right? It'll help, but it won't save you, because to inspect it and to be able to do that inspection, you're converting this back, but then you run into the same problem. The problem is that you are building this, everything is order 1, suddenly you've thrown in yet another order in here, yet another order in here, plus this order in, right? You can, and these things can sort of rack up. So in this case, you're sort of, you will still get some benefit, but but you won't get the outcome won't be linear necessarily. If your append operation or whatever your associative binary operation inspects within its arguments. Does that make sense? Yeah.
So you mentioned that in the example that you gave, the plus prime operation is function composition?
Yeah.
So is the definition of diff list that you had in the example, does that need to be specific to the operation that you want to make on the lists? Like, do you need to make
oh, I see.
The particular associative operation, because there's the plus plus within the to diff, right? So is this implementation of diff list specific to plus plus?
Well, no. With these three things, this can be used for anything, right?
Okay.
But the place where this will save you is for plus plus in certain cases. Plus plus is sort of interesting because depending on your use case, you may want to look within, because if you're just simply doing regular append, you're okay here. If you're just, so let me sort of pause here. So the process of doing this operation, once you've done this, once you've introduced an intermediate layer, once you have a derived data type, and you're doing this kind of processes, that's the build phase, the quote-unquote build phase that the paper talks about, right? Going from this derived back to base is the reflection, right? And you can do this reflection right at the end to get a concrete result, or do this transformation. But the reflection, as the paper uses it, is to do this transformation, inspect the intermediate representation while you haven't finished completing the full phase, right? So the definition of diff list here is sort of the regular diff list. This people use when you're trying to append lists. So it is with that. Why? Because in this case now, and we want this property, right? We want the property that this thing is cheap, because if this thing isn't cheap, then, or it's symmetric.
So I guess what I was wondering is, could you use the same implementation for diff list to do a CPS transform on some other associative operation on lists?
So what would be an example of different, like what are you trying to do?
I don't know. I can't think of. Maybe there aren't any.
Right.
Like I was thinking of multiplication for numbers, but for lists it wouldn't be associative. Maybe.
Yeah.
Or So just in general, like, are
Yeah,
these,
you can. Like you
Yeah.
can, as long as like you can use that diff list for essentially anything, right? Like, but I've already put some caveats. Is you will get a saving only when this operation doesn't inspect its arguments.
right, okay.
Once it starts inspecting its arguments, you will lose that saving that you just got. But you can still define that. Like you will still get some savings. Any other questions? Okay, so right, when this happens, you're kind of screwed here. And this is an example that the sort of tutorial gives, and I found this to be sort of a really natural example about when you would want to inspect, why would you want to inspect as well. And this is, if you guys take a look at the website, I'll provide a link to it. I'll also share it on the meetup page. It goes through this sort of series of examples going from basics of JSON data type that it creates and then adds these cases. But one of the cases that it adds, one of the things that it wants to do, and again, I've shamelessly copied, and this is supposed to be list of A instead of this, is, well, how do we show lists? How do we pretty print a list, right? When this is sort of the Haskell way of pretty printing, which is if I've got a list of 1, 2, 3, I want open bracket 1, 2, 3, close bracket, right? There's a problem here because at the end of the third, I don't want a comma again, right? Like all of us, we've implemented this in various forms. But there's a sort of simple, nice, elegant solution, which is this, which is, well, take a look at what X is. If X is, which is my input argument, if that's the empty list, just output is empty. We are easy, we are done, right? If it's a cons, however, it has to have a head and a tail. Good. Let's just call and pretend that the tail has been transformed, right? So the output of the tail is something. And so I'm calling show list T on the tail, and I'm decomposing it, right? So show list T, and this example, you can also see where the reflection is happening if you think about string being a list of characters, right? So I have a list of characters, that is what string is. I'm going from a list of A to a list of characters. My show list T is going to create a list of characters, okay? If I were to use a derived data type, this in this case would be sort of a diff list of characters. But then I'm inspecting it. I'm inspecting and breaking it down and looking at the head and looking at the tail, right? This head and tail, you don't get that in diff list. You only get that in the base, right? This view, this deconstruction, you don't get that in the derived data type. So once I've broken it down, what I say is, okay, whatever this P is, I'm going to place it here, right? Because at the base case, the P would be this open bracket, right? So this would sort of be the open bracket, that's how I'm beginning. And then I'm going to show my head, whatever that is. And then I'm going to add some stuff. And that some stuff depends. If this is just the end of it, that means my T was just nil. I will just close it. Then it's just S. If S is this close, then just close it. Otherwise, add a comma and then add S, right? So it's operating in this sort of, trying to do an intermediate result, trying to inspect that intermediate result without it's fully being done, and using that inspection to be able to define what the form is. Right, so this is an example, and this happens a lot. Like these patterns are pretty common in code base. It just takes a while for you to see this pattern. And the code example shows that. But when we are doing this, and if we were to do this now in the diff list realm, at this stage, we'd be kind of screwed, right? Because this is the point where this is coming in and saying, okay, I want to take a look here. I want to take a look at what I just did with my tail, and I want to dig deeper into it and see what's there. But you can't do that till the time that you run form diff.
Just to check my understanding, you could rewrite that to be columns H nil and special case that, right? Instead of doing that kind of like run show list T, could we add a second case in the middle or a third case?
Second case here or here, like.
Add a case after nil, but do columns H nil.
Okay.
Where you're saying if the tail is nil,
Yeah.
then you don't have to add a comma at the end.
Mhm.
Otherwise, you do.
Sure, yeah, you can do that. You can add other cases here if you want to specialize them, but what would you gain from that?
You wouldn't have to recursively call the shoelace.
You would. You still. You are unrolling the loop, essentially. That's what you're doing. Right? And yeah.
So you save the very last part.
I guess you'd save the condition.
Yeah. Well, so Haskell is lazy, so this condition is never really evaluated till it's needed. So yeah, in a strict language, you may want to do something different. Some of the performance implication may be different, but otherwise, the only thing that you're saving is to the extent that you unroll that loop.
Okay.
Oh, what did I do? Okay. And so what is the fix? The fix is mutually recursive data types. Now do I add other thing? No, I don't. So I'm going to have to apologize again. And I'm going to try and sort of paint a picture here in this example. So the problem that we were running into is if this plus or plus prime needs to inspect x, right, or the constructors of what shape does x have. And the reason that that's a problem is that there's a separation here. X is a recursive data type. It references x within itself. It doesn't reference anything else. X0, x1, both are of the same type, x. And I've created this derived data type. And this is just doing some transformation. This is simply, these are usually pretty simple. These are like the function that we saw. The codensity transform also sort of a similar thing. But it by itself it will have only sort of a single constructor, as it were. The derived data type is not very rich. It'll have one constructor which can have one or more arguments in it. And so the problem is that we want to avoid this from diff state, right? We want to avoid this from diff where I have to call from diff on this, go here, inspect, and come back. Now, we would be saved if there was some way to just inspect x0 and for us to get an answer, right? X prime rather. So if there was some way to inspect x prime and get the information that we need, then we are saved. But the information that we need is in essence the information about the constructors of x, right? So x and x prime need to be mutually recursive, and this is the game that the paper plays. It took me a while to really grok this pattern as to what was really happening here, and why sort of this would work. But that's the essence of it. Is the problem here is that this x prime, if you were to deconstruct it, nothing here references x. It's a completely different state. But if it were to reference x, and if x were to reference x prime, kind of a thing, then you'd be good. Actually, I misspoke. X prime does reference x, but x doesn't reference x prime. So, but let's look at an example. And this is where I did. Oh, we can go there. So it talks about the general technique and it calls these sort of view. So the X type that I just talked about, I call that sort of the base type, and it talks about the X prime. So this is the section where this is sort of the essence of what it is trying to do. So it says, okay, if I've got some base type, the general technique is create a derived data type, right? Create this X prime, and then the way you're defining and create a view type. Your view type is going to be the same way that you had your base type previously. It's just using a different name, and it's going to reference your actual efficient recursive type. We can go into this. We can go into what this applies. A quick example of this is this for the list or the tree. So it used tree. There was a regular tree data type, there was a leaf or a node. So the technique when applied was saying, well, we'll create a tree prime type, which is my intermediate representation. It is designed to be fast. It uses a bunch of tricks to do that. It actually piggybacks on efficient queues data structures. None of that is original work here, other than how to apply that to type-aligned sequences. I can comment on that, but that's not really important. So there's some way for you to have efficient sequence structures. And if you have that representation, that's my derived data type. I'm going to base my derived data type on that. But then I'm going to create a view instead of my regular tree type with just a leaf and a node. But this view type, it's not recursive, it's not self-recursive, right? In the node, in the references here, what it's referencing is really this efficient type. So my view type, which is my new sort of base type, because it's performing the same function, it's allowing me to deconstruct the tree into a leaf or a node. It's allowing me to deconstruct a list into a nil or a cons. However, in the cons, what I have is not a list, I have a diff list, or list prime rather, right? So it uses this mutual recursion to really run all the way through, so that when you're doing, you can then have so that this prime that you're having here, this plus prime can simply inspect x0 prime and x1 prime, and you're good. You don't need to go all the way back, right? That's really the trick. And he uses that, it runs sort of multiple examples. So I'm going to pause here. I am happy to talk about the various details in the sort of type-aligned sequences, how it does, what is the other stuff, or if you want to go into what are the applications of this, or what are the various examples, how useful or not is it going to be in sort of your day-to-day life or things, or how pervasive this idea is. So whichever way, happy to take questions. Yeah.
So I just have a question. I guess if you were to do this for lists,
yeah.
Would you have you have the derived data type and the view data type.
Mm-hmm.
So for the list, the base type, the definition is like it's nil or it's cons with a list or with some element of the type plus some list.
List prime, right? So if I'm going to do this transform.
But the base type remains the same, right?
The base type doesn't remain the same, and there's a reason why, because the base type is the full type of this. Let's look at what's happening.
So you
here.
would actually need to change the way that list is implemented in order for it to work with this mutually recursive solution? You wouldn't be able to just make an entirely
so you, okay, I understand. No, the answer is like you don't need to change the list, you can define, but how do you deal with lists? How do you, you can use their constructors, or you can use ways in which to combine lists, or ways in which, inject lists and things like that, right? So the paper provides an interface of an efficient sequence data structure. So it provides that, and it generalizes that to type-aligned sequences. A type-aligned sequence, very briefly, is so a sequence, a regular sequence, every element in the sequence has to have the same type, right? A type-aligned sequence says you can have different types, but they need to align themselves. If my first type is going from A to B, if it's a function, the second one has to be B to C, and then my type of this sequence is A to C, right? So it's creating these connected paths in the graph. But the paper provides implementation and provides the references to implementation for such efficient sequence data structure. But in that implementation, there are various functions that are provided. There's a function to view a sequence, which essentially means deconstruct it, or pop it, so take out the head. These are actually DQs, so you can take out the head, you can even take out the last element of it. You can create a sequence from a singleton. You can append, you can concatenate. And all of these are amortized order 1 complexity, or they can even be using Tarjan's implementation, order 1 worst complexity, right? So the entire benefit here is all of these things were done previously. We came up with efficient sequence types, we came up with efficient sequence structures, but there was no principled way to be able to piggyback on the effort that had been done there, on the performance gains that had been done there. So what the paper does is provides a way, really concrete way, and provides different applications saying, okay, we've done all this work. Tarjan and other bigwigs have come up with efficient way to implement these things, but now their entire stuff we can simply just stand on their shoulders and use this. And the way they do that is you define all your operations not in terms of the constructors. You define them in terms of view. You define them in terms of or an append or things like that. And if your entire program is based only in that form, then you don't care what the base type is, right? That's how you play this trick of what the base or intermediate type is, because your program is not looking at it. Your program is just being defined in terms of that associative binary operation, right? So if your associative binary operation is an append, that's fine. You will now have an append which is working on this efficient structure, or rather, you will have an append which works on this list view type, right?
Okay, so you would make it so that the base type, instead of being like what's on the screen right now, would be like with the list view.
List prime.
Or list, so the derived one?
Yeah, exactly.
Right. And
So the self-reference has been replaced with the reference to the efficient one.
Right. And then the view is the one, the view type is the one that it looks like.
This is the view type. This would be the view type.
Oh, okay. So
Yeah.
then you only ever deal with the view type and the derived type.
Exactly. And
Okay.
or rather, you only ever deal with the derived type, because within the derived type,
Right.
you are the derived type only has one constructor, and that constructor is giving you enough information. It's capturing it. It's holding it ready so that you can inspect it. You
Okay.
never within that operation.
Okay. Okay, got it.
For the benefit of others, I think. And by the way, feel free to ask questions. Let me give you sort of a concrete example here. So, right. So this is what I was talking about of having an interface. Ooh, that's what's happening. Something weird happened. Phone crashed. Yeah, it did. Okay. So in this case, if you take a look at the top, right, the empty singleton, the append, and the view, right, on the sequence class that it's defining, that's sort of just think of it as an abstract interface. Forget about the types. Doesn't really matter. And then he's creating sort of a type-lined sequence and providing what the meaning is there. And in this case, essentially this abstract efficient sequence, you only ever deal with it in terms of these functions. So you in your program, if you're writing things, in your implementation of plus prime, as it were, you use the empty function. You will use the singleton function. You will use this append function. You will use this view function to inspect. And that's all you're going to ever do. And this will work for less. If you want things which are for monads and things like that, where the append operation is actually Kleist composition, it's not. It's still dealing with the same shape, but each argument is of the type A to MB. So it's each argument is a function, right? And a function has two types at least. It's going from input to output, right? So you need something which is more general, which is this type-aligned sequence. And in here, essentially all you will see is, well, an empty is a path. An empty is just an empty thing. It's an empty path. So it can be path from any x to any x, just itself. It's a self path, as it were. A singleton is, you just have an edge, really. You take this is C edge. It's an edge from x to y, or function from x to y. And I'm just saying, okay, I'm going to take that and I'm going to pretend that I've got a path from x to y. It's just a path of one length. I can do an append which says if I have a path from x to y and I have a path from y to z, then I've got a path from x to z. And I can do a view of it which says if I've got a path from x to y, then I should be able to sort of view it, and in the view I can inspect whether it's empty or if there's more, right? So these are the basic primitives that the paper provides, that the paper sort of provides a reference to. And the implementation of this is simply rewrapping functional data structures, efficient functional data structure, right? The only thing happening here is just providing this unified interface. That's the only magic which is happening here. Similarly on this side, if you're doing regular sequences, you end up with view. In the view, you can see if it's empty or if it's a head or tail. And this solves the problem. This solves the problem of the continuous CVS transform that we saw, because now, in order to inspect, I only need to call in viewL, and I'm good, right? Just by calling viewL, I'm okay, but viewL is order 1 by this implementation. And this type viewL is also order 1, right? So it's almost like a lot of magic is happening, but then no real magic is happening, because all the magic is happening in rewiring and using other people's stuff that they've done in this entire exercise, right? It's kind of clever in that. Because when you take a look at the code, and I was looking like, why does this work? Well, it works because all of these are order 1. So sure, it'll work. And if you go back, sorry. Right, so in this example, the way they go about in Monads, are people here familiar with Monads at all, or no? A little bit? Okay, well, skip it then. But the Monad is, it basically talks about an interface, right? So if you are thinking about a list and you want append, the append is really the core of it. That associative binary operation is really the core of it, and you want to make that efficient. That's your plus prime. You define prime. But to the extent, but this is all library implementation detail. Users of your library. So if you are a library of your own awesome logger, right? I'm writing a logging library which uses appends to concatenate things together to create this log. I want this log processing to be fast. The users of my logging library don't need to care. They will just call log.append and everything is good. It's me internally as a library developer that I'm playing these tricks. It's the same way if you're writing your own sort of monad. If you're using that monad or using sort of some interface, you may not care about this because the interface is already provided. But as a person who writes interfaces for others, this technique is really useful. And he's applied that to the free monad, to a bunch of other, but because it's applied to the free monad, it applies to all monads, and so you can just do it once and just use it and forget about it, kind of thing, right? So this is one of those gems of a paper where it's amazing, but you probably never need to care about it other than the fact that he's doing something quite beautiful. So, yeah. Any other questions? I'm going to try and see if I can bring back. Nope, that's gone.
So is this stuff, like, if you use Haskell and you use the standard library, are you using this stuff?
The standard library doesn't have it, yeah.
Or like the sequence type classes you showed.
Yeah.
Like, and I guess if you're doing, I guess, like, do you come across this in regular Haskell code, or do people have to kind of?
No, right. So, well, the sequence type, the implementation of data.sequence in Haskell provides similar, not as great asymptotics as this one does. It provides amortized order 1 for empty. It provides amortized order 1 for singleton. It provides order 1 for viewL. Append is ordered log, so it's logarithmic in complexity. That's simply an implementation. There is a library in Haskell which uses which is called typeline. There's a GitHub repo which uses. There's a book which is based off of PhD thesis by Chris Okazaki. So if you're interested in functional programming, if you're interested in functional data structures, that's a great thesis or paper to go through. And that outlines a lot of the techniques used to implement these efficient sequences. But that's been done, that's on a GitHub repo. I know about it because as a maintainer of the extensible effects library, people were requesting, oh, does this have the reflection without remorse, optimization? I was like, nope. Okay, I guess I'll put it there, right? And so
this, as a library maintainer, then
this comes in handy.
This is something that you can incorporate, and your users don't need to care.
Nope, not at all.
Okay, cool. So
Right.
So you end up taking it. Basically, you can you have this transform that kind of transparently turns things into right associative so that it is more efficient, and it's just kind of like you do some work to do this trick, and then your users can.
Well, you aren't
take
even
advantage.
turning it into right associative. You've turned it something which was asymmetric into something which is symmetric and fast. The derived data type is an efficient double-ended queue, right, catenable, which can be appended, and that's what you're using as your intermediate representation.
Okay.
Right? So the entire premise of this paper is going back to it. So it's good for a couple of things. I would urge people to read this paper if they can't think of very many situations where sequences arise, because this gives you very diverse examples of where such sequences arise. Lists are not the only thing, JSONs are not the only thing. Just regular programming patterns can be seen as sequences. And the reason they can be seen as sequences is if you're thinking about pure programming, you stop thinking about doing code which does things, and you start thinking about doing codes which describes things. And that description, well, you can have a list of descriptions. You can have a log of descriptions. And so anything can have a description of it, and because you have a description of it, sequences arise, right? And so in all of that, that common thread, users of that, if I'm providing a library which does some function, and in my internal stuff, I'm describing the things that I do, I can use this optimization for the library to be fast. The users of the library don't need to care. I would go even further to say that even library developers actually don't need to care about this technique, other than the fact that it exists and for you to simply use it. If you are writing a lot of your interfaces, if you're doing a lot of things like a state monad, or if you're doing other effects and things like that, you can simply use those libraries which use this, right? So it's sort of libraries all the way down. It has been incorporated at one level, and there's the effect handler, the algebraic extensible effects which uses it. There are, I think, I haven't broken down the free representation there, but that can be a separate package. And if that's a separate package, people, when they want to use a free monad, can simply use that and don't need to worry about what's happening behind the scenes. It'll just be faster, right? So even library writers don't need to know about it unless they're working at that base level. Cool. If no more questions, I will paste the link to this. And again, apologies for the poor presentation.